All right, so what we will do in the next few podcasts is to look at the specific ocean circulations. We looked at the big global picture and we mentioned some specific western boundary currents, eastern boundary currents, special circulation in the Indian Ocean, and so on. Now we will pay a little bit closer attention to some of the features, and then I will pull up one animation from NASA that shows how the real world actually works in terms of ocean circulation. So I've mentioned several times that the Southern Ocean is special because it has no zonal boundaries. It's a complete channel. And I had also mentioned several times that the winds are blowing from east to west or west to east. Oceans have boundaries, and this kind of limits the amount of energy that can go into the ocean, which we mentioned is 2 to 5%. On the other hand, since the Southern Ocean is a channel, winds can keep on churning it. What will be the limitation? Obviously, the Ekman currents or the wind-driven currents, which we said remain mostly trapped above the thermocline or the pycnocline in the subtropical gyres and so on. In the Southern Ocean, it can go pretty deep and can hit the bottom. The bottom friction can become the limitation for further energy input into the ocean. So the main features here are the Antarctic Circumpolar current, one of the more famous currents. It's also known as the west wind drift, and it's the only current to completely go around the Earth because of the special channel configuration of this ocean. And this obviously moves more water in terms of sphere drips, the transport, than any other current in the world, right? So look at this figure carefully. It is showing multiple convergences and divergences. I hope by now you are comfortable with the terminology convergence of currents and divergence of currents. We often also talk about Ekman convergence and Ekman divergence because they are wind-driven convergences and wind-driven divergences. Okay, so the subtropical convergence zone happens at the outer edge where the mid-latitude westerlies are meeting the polar winds, remembering that this is a special polar region. And then you have the Antarctic convergence shown with these blue dots in the middle, right? So the Antarctic continent, which is sitting at the center, is land, has a lot of glaciers, very cold temperatures, and around the Antarctic continent you have obviously east wind drift because we have polar easterlies. Remember, high pressure on the pole, low pressure around, winds going out, add Coriolis, and so on. So you have east wind drift. You can see the main names that will come up again and again, Ross Sea and Weddell Sea here. So you have the Antarctic Circumpolar current outside, or the west wind drift, and you have the east wind drift in the middle, which means the east wind drift is being turned to the left, west wind drift is being turned to the left. So you have a divergence in the middle. So you have Antarctic divergence shown with this kind of a dumbbell shaped thing, or arrows on both sides. So you have upwelling being forced in the open ocean because there is divergence happening on either side. So the Antarctic convergence obviously has cold, dense Antarctic waters, warmer, and they are less dense than the sub-Antarctic waters, and that's kind of the northernmost boundary of the Antarctic Ocean, or the Southern Ocean. Okay, east wind drift is created by the polar easterlies, so it creates surface divergence along with the west wind drift, and you have the Antarctic divergence bringing up cold waters, nutrients, abundance of marine life. But it depends on whether you are to the south of the polar circle or to the north. If you're to the south of the polar circle, then you are going to have 6 months of sunlight and 6 months of darkness. So when the production happens depends on when the light is available, right? It's not just the nutrients. You will also need lights for life to occur. So we'll look more at the Antarctic continent in the context of climate change, glacier melt, loss of shelf ice, and so on. Needless to say, Antarctica is a critical player in global warming. Also was the region which first had the ozone hole because of a very specific circulation which traps the air that comes in. So it was receiving the chlorine and was trapping it inside, and the reactions were reducing ozone and creating the ozone hole. So Antarctica is important for storing so much glacier, which if it melts, it's going to raise the sea level by a lot. Plus, it's a very critical component of maintaining Earth's temperature,